Z is the charge divided by atomic number. Turn off the volume. And then you can have electron beams which are scattering on the proton beams, which are up to 18 GeV. Okay, so this is a very high energy collider and has a center mass energy range from 20 to 140 GeV. So it's a wide range of energies. And the truly unusual thing about this collider is that its luminosity is very, very high. So it's about 1,000 times that of a previous collider. So this was Hera at Daisy. That had luminosities of 10 to the 31. And so this is 1,000 times more intense. And so you can ask much more differential questions about various things in QCD than you ever did before. So it's really, in that sense, the ultimate QCD machine, which can really do very high precision experiments. And so what is measured? So what we're measuring specifically is that you're doing a deep elastic scattering experiment. So you have a polarized electron, which scatters of a polarized proton. Right? So the spin of the proton is can be either aligned along the direction of the electron, or it can be anti-aligned to it. And so what you do is you measure the difference in the cross sections for the scattering process. And so the difference in the cross sections is an asymmetry, and then you can define an object called a structure function, which is really this related to this asymmetry. So it's a purely experimental object, right? It's a difference in cross sections that you measure. And you can show that this object, the quark helicity that I mentioned to you before, which is 30%, is the integral of this structure function, this asymmetry, so this cross section. It's the first moment of this distribution, okay, in X, where X is this Bjorkian X value that you measure in deep elastic scattering experiments. And so this is the data that exists so far in polarized deep elastic scattering, from which we deduce that the proton's helicity is very small. And this is all the data that will be provided by EIC, for the Electron-Ion Collider. And the yellow shows the uncertainties just from projections using randomization group equations as to what these uncertainties will be at high energies. And you'll have data in all of these points here as you go to high energies. And so the current uncertainties in the gluon distribution, which are very large because of the limited data, will really shrink tremendously. So you will really be able to extract, as a function of X or energy, the contribution to the gluon spin at that given value of X, very high precision.
What is delta in that equation?
So that's just a, yeah, so it's just a question of terminology. Sometimes the quark spin is referred to delta sigma or sigma. And so delta is the reason it's used as delta is because if you think in terms of the parton model, then what the quark helicity is measuring is a difference between the number of left-handed and right-handed quarks. So it's an asymmetry. So if you think of a proton that's polarized in this direction, and so you're saying how many quarks in the proton have spin aligned along the direction of the proton, or how many have anti-aligned. So that's the delta. While when you measure a usual structure function, it's just the total number of quarks and gluons in protons. So that's the terminology. Thanks for the question.
And that asymmetry is really the definition of the delta sigma.
Yes. So there's a so this is a purely experimental definition, if you like. Okay. There's a subtlety to this in the sense that G1 contains flavor non-singlet and flavor singlet contributions. And when I refer to delta sigma, I am talking about just the flavor singlet component of G1. So it has no distinction in up, down, and strange quarks. So that's the definition. However, this will have a clear operator definition, which I'll come to in a second. But before I go there, I just want to mention the power of this EIC machine, that if you look at this structure function, this asymmetry G1, as a function of X and Q squared as a function of X, then you see that as you go to small x, right, you have all this additional data, that's going to really constrain all these different theoretical projections that one has from existing data. So in principle, how this behaves as you go to smaller x or higher energies for a fixed resolution is highly unconstrained. There's some Regge kind of motivated ideas, but it's in general, it's very poorly constrained. And so when you have all this data, it's really going to limit what this value of G1 is. And so this is shown in terms of the uncertainty of the gluon spin, which is the integral over x, is delta G, the gluon distribution, and the quark helicity distribution. And you see that the current uncertainty is huge. Okay, basically, we know very little. And once this experiment turns on, you can really reduce it to this very, very small uncertainty. So you can really learn about the gluonic contributions to proton spin and the quark contributions. Now, with regard to this question that was asked, in the parton model, as I mentioned, G1 can be thought of as 1/2 the sum over all the flavors, the charges of all the flavors squared, times the sum of the difference in the left-handed and right-handed parton distributions instead of proton. So that plus that of antiquarks. Okay? And that summed over all the charges of all the different flavors is what G1 is. Now, sigma is really the democratic addition of these guys, okay, without the different weights of the flavors. So that's the difference between the singlet and the non-singlet contributions to G1. So
W mu nu the stress tensor.
Sorry?
W mu nu the stress tensor.
So W mu nu, no. So I'll come to that in one of the next slides. That's the antisymmetric part of the current correlator. And that's why I said it's not the stress tensor, it's the current correlator that really we're sensitive to, which tells you something about this object that you measure in experiments. And so most generally, this G1 is this transverse projection in terms of these Levi-Civita tensors on the antisymmetric part of the current correlator. Okay, so why is this interesting? So as I said, the first moment of this measurement can be related to a non-singlet contribution, and this is weak decay physics. So this 3F plus T is related to, yeah.
What was that? Previous page you had an axion mu nu.
Yeah, so this is just a transverse Levi-Civita. So it's just a transverse projection to extract this.
So epsilon has 4 indices, right?
So this is just a transverse projection on this W mu nu. So the antisymmetric part of W mu nu. So I will show you the most general expression, and if I just act on this with this 2D projection, I recover this structure function G1. So it's just the antisymmetric Levi-Civita tensor
in 2 dimensions.
Of the 2 dimensions.
And these 2 dimensions are the 2 transverse dimensions.
Yes. Okay, so what I was saying is that this sigma here, the isosinglet part of G1, so remember in the parton model, it's just the sum of the isosinglet sum of the quark projected one way or the other way in the proton. So this sigma times the spin 4 vector is nothing but the isosinglet axial vector current in the proton, the polarized proton. So this quark helicity can be directly related to this isosinglet axial vector current. And so now this is very interesting, obviously, because we know that from the anomaly, right, you have this anomaly equation here, where the divergence of the axial vector current can be related to 2 times the number of flavors times the divergence of the Chern-Simons current, us, plus a pseudoscalar contribution proportional to the quark masses.
And so, to relate to Ivan's question, because what Ivan was saying, in any field theory, right, the total spin is expressed through T mu nu.
Sure.
So somehow here,
right,
this observable kind of measures, we're pretending that gluons are not there, right? And we're pretending kind
No, you're not pretending that they're not there. I'm just saying what you're measuring is, as I said, you can measure a current correlator, right? And I'll come to the more general expression in a minute. And so when you measure the current correlator, that's what you do in deep elastic scattering, right? And so that is then can be written in something that's directly proportional to just this component of the current. That doesn't mean that the other components don't exist. Right? I'm just extracting this. But I understand that the overall spin sum rule, and that's I think your question really comes in terms of can be expressed in terms of spin tensor.
I was only asking about the definition of spin.
Yeah,
There's only one definition of spin that I know.
Yeah, that's
the quantum number that's measured by the stress
that's the
tensor.
overall. So that's what actually gives you the sum rule.
That's what I was
Yeah.
talking
Okay.
about.
Sorry. Yes. So I mean, in general, I would also think about it in terms of the angular momentum tensor as well, right? So I would most general definition of
The
conservation.
angular
of
momentum tensor is coming from T mu nu
Right,
times
exactly.
x0 and antisymmetric.
Exactly.
mu.
Exactly. And that's how you derive the spin sum rule in the first place.
That's right. That's right.
Then why do you call this?
Sorry, I misunderstood your question.
No, but then you
Yeah.
you are trying to say that there's another notion of spin.
No, I'm saying the quark, just helicity. I'm just talking about the quark helicity alone, so which is one component of all the possible contributions.
That's precisely what I was saying.
Yeah.
at the beginning.
Yeah, so that's what I meant by saying that pretended, like, basically you look at the quark
Exactly. That's what I meant by the term in the stress tensor.
Right.
Okay, I understand now. Okay. Yeah. So in fact, that's how you derive actually the spin sum rule in the first place. Is within the, you add it further. Sorry? Oh, okay. Yeah. So yeah, I'm just talking about, and not only I'm only talking about this isosinglet component, this first moment, right? And so bottom line is that this quark helicity is related to the anomaly. So it's related to the divergence that shows current, which is proportional to the topological charge. So the virtue in doing such experiments is really you're learning something about the real-time dynamics of the anomaly, which is fairly non-trivial. So what I'm going to do is I'm going to talk about this. So there's many subtle things that come in when you try to take this seriously. And what I'm going to discuss this is within the context of the Orline formulation of quantum field theory. And so in terms of thinking in terms of amplitudes, this is equivalent to this string amplitude formalism, which has been a very powerful way to compute multi-leg loop diagrams in QCD. This equivalence was shown by Strassler, and it's also very useful because it provides a very powerful first quantized intuition that's going on. And my collaborators and I found that this is also a very powerful way to think in terms of how you formulate infrared safe S matrices and QED and so on, and sort of motivated by some of the work of Monica here and others, sort of thinking about some of these problems. So it's a very useful and powerful formalism for a variety of interesting problems. And so in particular, if you think of in terms of the famous chiral anomaly, okay, here, this is quite an expert audience, so you probably know what the chiral anomaly is. So essentially, it sort of comes from this kind of triangle operator, which is an axial vector field insertion, and then two vector fields here at bottom, this kind of triangular. So it's a 3-point correlator, so it's a VVA correlator, as you call it. And its primary feature is that it's proportional to f of dual. So if you compute this in QED or in QCD, you find that it's proportional to f of dual. And then it has a structure which is L kappa, which is the Lorentz index divided by L squared, where L is the sum of these four momenta K2 and K4. So it's in some sense it's a Mandelstam T variable, if you like. Okay, so these are K2 and K4 are the four vectors, or the two gluons or photons that are going into this. And so L is a measure of the off-forwardness of this object here. And the remarkable thing about this is that this object is robust to all orders in perturbation theory. That's something called the Bardeen theorem, the Adler-Bardeen theorem. So it was first discussed by Adler and Bardeen in the context of QED. And there's a beautiful paper by Bardeen where he showed that it's also one loop exact in QCD. So in other words, you could dress the triangle with all numbers of gluons, and this operator structure is robust. Now, of course, as many of you probably know, that another way of thinking about this is that the anomaly arises from the non-invariance of the path integral measure under chiral rotations. Okay, so in other words, if you say that the measure, so this is the Wess-Zumino action where you have the QC Lagrangian, and then you add all possible sources and fields, here, sources and currents, right? So you have axial vector, scalar, you have a theta term, times topological charge density, you can have pseudoscalar and scalar sources. And the A index represents a flavor index. So if you're talking about QCD, you have SU3 flavor. And so the way you think about the anomaly in this context is you can take the functional integral of this generating functional in terms of these external sources. And what that gives you is the following kind of functional differential equation here, which contains all the anomalous functional Ward entities to all orders. So these have to be satisfied by any kind of effective description that you have. And this was already articulated by Wess-Zumino a long time ago. So this is very powerful. And so here you see, for example, dB/dV5, right? And so this is the anomaly equation here. But if you turn on quark masses, then you have a very non-trivial mixing between the flavor singlet and octet sectors of the theory, which is very interesting. And so this constrains a lot of low energy dynamics in QCD, this functional water energy. So here's an example, and I personally think that Adler deserves a Nobel Prize for this work, because here's the famous contribution of the ABJ anomaly to pi naught to gamma. So this is the most striking example of the relevance of topology to the physical world, is this decay here, pions to photons. And so here's the lifetime of this decay in 10 to the minus 16 seconds. And that's plotted as a function of, this is Adler's prediction here. Okay, so this solid line is his prediction, this is just this one loop calculation here. And this is a function of time. And these are experimental data. Right? And you see that this has remained unchanged, of course, and you see the experimental data has kind of converged to this value here. And in fact, the dashed line is all the higher order chiral corrections to Adler's result. They change it by 4%. Okay? And so that's still within the error bars of this remarkable result. And by the way, there's a folklore that pi naught to gamma fixes the number of colors in QCD, and that's not true, actually. It doesn't fix it. You need to look at other anomalous decays to do it. Now, so the striking thing, of course, is that the chiral limit, right, in the case of massless quarks, the pi naught does not decay, okay, without the anomaly. Okay, this is the Sutherland-Weltman theorem. So the pi naught does not decay at all. And if you introduce quark masses, usual chiral perturbation theory would give you a lifetime which is 1,000 times greater than that measured in the experiment. So the anomaly gives you sort of 1% accuracy in QCD for something really fundamental, and without which you would be off by a factor of 1,000. So this is, if anyone were to say, well, why is topology of the QCD vacuum relevant for the physical world? This is as striking an example as any. And what I'm going to talk about is another reason why topology matters. And so, but before we go there, I just want to talk about how one would think about anomalies in the Worldline formulation of quantum field theory. And so the simplest way to think about this is you think about your fermion action. So here's your Dirac action. And where you couple Dirac fields to scalars, pseudoscalars that supply here, gauge and axial vector fields as represented by this B slash. And where your Dirac operator now in the presence of these fields can be represented in this way here. So the effective action corresponding to this is the log of the determinant of D slash. Dirac operator. In the presence of being saturated by these arbitrary vector, axial vector, scalar, and pseudoscalar fields. Now you can just do a simple trick where you split this into real and imaginary parts. And the imaginary part is just a phase of the Dirac determinant. And the entire dynamics of the anomaly comes from this imaginary part, right, the phase of the determinant. Now, you can just work with the real part, and you can use this famous Schwinger trick and write down the effective action as an integral or a proper time variable with some normalization. And then these bosonic and Grassmannian point-like variables. So these are not fields, these are actual quantum variables, just like quantum mechanics. And so where these objects have periodic and these have anti-periodic boundary conditions, with a Whirlline action, which for left and right-handed fermions can be written in this form here, where this is epsilon is the I-mine, this is the kinetic terms for the bosonic and fermionic fields, and then this is like the Wilson line term, and then there's a split precession term. Now you can do the same thing remarkably also for the imaginary part of the Whirlline action. This is a very beautiful, not as noticed figure by Venugopalan and Raju, where they showed that this imaginary part can also be expressed as a Whirlline Lagrangian, these bosonic and Grassmannian fields, where this phase can be written also in terms of such a Whirlline action, just exactly analogous to the one for the real case, except there is a parameter here, alpha, which explicitly breaks chiral symmetry for all values between -1 and +1. So it's essential to do this in order to get a regularized expression for this imaginary part. And then, in addition, both these bosonic and fermionic fields, so they have periodic boundary conditions, and there's a non-trivial Jacobian, and that's just Jacobian for zero modes. Where you separate out the zero modes, you write down this expression, and multiplied by G value factor.
So how to think about that? Because that looks like it's very non-local, right? One is averaging over this alpha,
Yes, yes.
which stands in front of the exponent. So
Yes.
it's like averaging over.
Yes.
Coupling
So this is
of-
just a formal rewriting of this phase of the determinant. So it's just an attractive way to write it, and it's kind of remarkable. It has this kind of Lagrangian-like form in terms of these point-like objects.
Can I show?
Oh, sorry. Go back. Yeah. I didn't write it out explicitly.
And alpha is just some coupling which appears.
Alpha is just something that appears in the coupling of the pseudoscalar and axial vector fields to the Dirac.
Does it appear linearly?
Sorry?
Does it appear linearly?
Sorry.
Does it appear
Yes,
linearly?
yes. So it's just a parameter that goes between 0 and 1. So it's just a formal way to rewrite this.
But if I take explicitly integral over alpha,
Right.
then I will get something which looks like very non-local
Yeah.
time
Yeah.
action, right?
Yeah.
So
You use some delta function.
Sorry?
It's periodic alpha.
do you have
It's like
explicit
angle.
form for that alpha?
I don't have the explicit form. So because, that's a separate talk. I mean, I can give a separate talk. I just want to get to where I'm going. So,
Okay.
and that would be, but okay. So let me just give a very simple example where I just look at now the anomaly in the Whirlline formulas, and you see it's a very simple derivation. If you try to do it using Feynman diagrams, it's very complicated. It involves point splitting and treating gamma 5 properly. If you just look at the one loop effect of action, and now I've written the background axial vector field as this A5. And so again, here are my bosonic and Grassmannian path integrals. These are the kinetic terms. I have the Wilson line terms, spin precession. And now I've taken the terms for the measure and I've kind of re-exponentiated them in this fashion here in terms of these A5 fields. So if I turn off the background axial vector field, then these are just 0. Now, if I take the functional derivative of this object with respect to A5, that's nothing but this isosinglet current as it couples to A5. And if I set that equal to 0, this is my anomaly result. Okay, so this is a very beautiful, simple way to derive the anomaly equation just using this Whirlline formula.
Sorry, where is this alpha thing here?
So I think that's the thing. So the interesting thing is that particular representation, right, is unique to the Hooker and Gagné's formulation and while it's not essential actually. So this is an alternative formulation in terms of McHugh and Schubert, where they did not employ this so essentially what de Hooker and Gagné did is they went to this 8-component formalism where they doubled the Dirac matrices into an 8 components, and you have 6 Dirac matrices that satisfy closed algebra. So it's a very specific realization of this heat kernel representation. While this is a much less formal, I think, framework where they did not have such things as you currently point out, but they were still able to. This is an alternative expression of the role of the phase of the determinant. So, for example, if you go and look at Polikov's book and see his derivation, it doesn't involve any of this fancy stuff with this alpha. But that turns out to be very valuable in what I'm going to come to discuss. Okay, so this is just a cheap and dirty way to derive the Carl anomaly. You don't need any of that additional sophistication, but that sophistication becomes relevant when you think about other Wess-Zumino-Witten terms. Because this expression is really kind of the correct way to do it in sort of this heat kernel regularized fashion. Okay, so now I come to this object that I was talking about here. So if you think about the hadron tensor and deep elastic scattering, that's just the correlator of currents, and that's actually what was my confusion when you asked the question. So you're measuring essentially this hadron tensor, which is the correlator of current. So imagine you have a virtual photon that scatters of your objects inside a proton, and so you're looking at correlate of 2 such currents at 2 different space-time positions. So this is definitely a Minkowski object, 2 different space-time points. And what one wants to look at is the anti-symmetric part of this guy. Okay? And that can be written in this form here. And so to extract G1, like I was saying earlier, that's why if you have this transverse projection of the Levi-Civita, that really picks out this G1 component here. But this is the most general expression you can write. And these are these structure functions, or the asymmetry in your cross sections that you measure. So this is a purely experimental definition, right? You can do the deep elastic scattering experiment. You can define all these objects and really extract these fundamental quantities from the experiments. Now, where does this whole business with Warlines comes in is that this G1 object, right, is proportional to polarization tensor. It's this antisymmetric part of this object here. And that, in perturbation theory, can be thought of as this box diagram. So you might have heard about G-2 and so on that people talk about. In G-2 also you're measuring this light by light kind of scattering, except now here I have 2 gluons. And these are all off forward. So this is an exact kinematics where K1, K2, K3, and K4 are full, 4 vectors without any approximations. And so this is this general box diagram. And you can write down this box diagram in this Warline formalism, this very explicit form. And now if you take then the high energy limit, so this is so-called Bjorkian limit in QCD, then you can actually calculate what the structure looks like. And similarly, you can take the Raju limit, which is small x, high energies, fixed q squared. And so what is remarkable is that you find that in both cases, inside the box diagram, you have embedded triangle. In other words, you can compute this in very different limits. You find that the structure function here is proportional to the anomaly pole, okay, times f of dual. But these are slightly different light cone positions, but you are integrating over all of that. You see that you have the same kind of structure. And this pole is sometimes called the Kogut-Susskind pole in the literature. And the question is, how do you understand this, right? Because you're doing an experiment, and I'm taking the forward limit of the experiment to extract a cross section or a difference in cross sections. And so in the limit, this goes to 0. This gives me something that's going up. How do I understand this? Okay, how is this pole regulated in the QCD? Okay, because it's a physical limit. The forward limit is a physical limit, so t going to 0 should give you a cross section, and you're finding that there's a pole sitting there. Okay, and so this actually turned out that this is really very interesting in several ways, is that this problem of computing the spin of the proton, which is the G1 here, right? This is the integral of this is related with quark helicity. This is deeply related to the UA1 problem, QCD, which is put simply, why is there no isosinglet Goldstone boson in QCD, or equivalently, why is eta-prime so massive? And the first people to realize that there's some such connection, actually no, it was first realized by Venugopalan, but then Jaffe and Manohar discussed this extensively in a well-known paper more than 30 years ago. And they argued that, and so a lot of people were doing perturbative QCD calculations of these kinds of box diagrams, and they were missing this pole. Okay, so they were doing these calculations, they were doing exactly this calculation using Feynman diagrams, and they didn't find this pole at all. And the reason is because they were making collinear or high energy approximations of this result, and so they didn't find this pole at all. However, you have to do it in exact kinematics, where you keep all the four vectors of these guys. And to our shock, this calculation had never been done in QCD. It's a one-loop calculation, okay, and in exact kinematics. And people have done, of course, very sophisticated calculations, but they've never done it. And until we did it first in this Warline formulation. And so you see that there is this issue here. And so this was actually something that Venugopalan really, he understood the problem fully. Okay? He was the only person in the entire literature that we discovered who actually understood what was going on. And this is him wearing his Dirac medal, of course. And what is remarkable to me, and so I'd never worked on this problem before, so I started working on this during the pandemic. I've never thought about spin at all before. And of course, you know, Venugopalan is a giant in physics, as you know, and to my shock, his work was completely ignored by the entire perturbative QCD literature. So his paper, his most cited paper, had only 30 citations since 2000. And our paper was one of the first paper in 12 years to cite his paper. And so it's still a big surprise to me. So there are actually textbooks that are written on spin which have no mention of his work. So it's kind of a sociologically interesting question. Anyway, so at the very least, what I hope is we resuscitate his beautiful work. Now, the difference is if you read his papers, they're almost unreadable. Okay? So unless you're really well versed in the language of Legendre transforms and so on, it's a very hard paper to read. But we realize that the essential physics can be encapsulated in the following fact. So if you really work out the phase of the determinant in terms of this object here, and then you calculate explicitly, which is what we did, you find that there is such a Wess-Zumino-Witten term here, coming from the phase of the determinant, just like pi naught to gamma. And that's a massless pseudoscalar eta bar coupling to FF dual. Omega is FF dual in my language. And F is the eta bar decay constant, which is 1 over square root of NC. So there's a 1 over square root of NC factor here times eta bar times omega. And we derived this explicitly using this Warline formulation, and we found to our pleasure that this agreed with the expression that was derived in Carl perturbation theory by Kaiser and Lloyd-Wheeler, even though they just wrote it down by symmetry arguments. And by the way, you can derive exactly this expression, similar expression for pi naught to gamma in the Warline formalism. And that's what De Hoek and Gagnon also showed a long time ago. And so essentially, what we are arguing is that a lot of this dynamics can be understood in the following kind of Warline, in following effective action for this eta bar, where you have this kinetic term for this Goldstone, and then you have the usual theta term, QCD, theta times F dual, and then you have this Wess-Zumino term here, and this is the topological susceptibility of Yang-Mills. So of course, you take a second functional derivative, that's going to give you defined Yang-Mills. Now, since theta is not dynamical, you can just get rid of it from the equations of motion. Okay? And this is kind of your axion-like effective action that you get. And then you can do a field redefinition, and you see that, voila, you get the massive eta prime, okay, with a non-propagating detail. Okay, so this is just another way of saying is that in the massless limit, the eta prime is the QCD axiom. So how many people knew this? I mean, this is something, you know, in the chiral limit, there is an axion in QCD, and that's the eta prime. And of course, it's also in large MC. Okay. So it's large NC limit, but not MC equal to infinity that you have. And so this is exactly the same physics that goes through.
What you mean using the equations of motion? Which equations of motion?
Well, I mean, I can just take, the saddle point of this object here, and you see that
with respect to which variable?
Say with respect to theta.
So
Right? There's no
theta-
kinetic, so there's no momentum conjugate of the theta.
But so
right?
theta is not a constant. You are minimizing
Yes,
with respect
yes,
to theta.
yeah.
Um,
Principle, yes.
And isn't that the same as introducing an axiom? Because I mean, normally theta is a number, right? And it's fixed by nature to be whatever it is, but
Yeah, no,
close
but
to zero. But here instead you are trying to find the minimum with respect, varying with respect to all the possible theta, right?
Right,
It's
but
not what you do in QCD without axioms. I
well,
mean, the axioms are there precisely to minimize with
so
respect to theta.
QCD without axis. So in the chiral limit, right? All I'm saying is in the chiral limit, you can absorb the contributions from the phase, right, into the kinetic term, right? There's no genuine theta term in QCD in chiral limit. So the theta times FF dual term by field redefinition, right, can be absorbed completely into the Dirac term.
So you can set theta to zero.
Or you can integrate over it. I think that's
Yeah, exactly.
Given that it doesn't depend on theta, you can
It doesn't
integrate.
depend on
You
theta
can
at
integrate
all.
on theta.
But then you have something that depends on theta because look,
Yeah, no, this expression doesn't depend on theta at all. So that's my point. So it's at the end of the day, you can formulate it in this way, and then there's a shift relation that you can employ. So you can just shift theta. You can
because
think
that's
of it
not
as
the
shift
complete action.
symmetry.
There is something else beside. There is also the fermion part, right?
This is the phase of the fermionic determinant, essentially, right? Remember that the way you derive the Wess-Zumino-Witten term is from the phase of the determinant. So this term is coming from the phase of the determinant. And so because you have such a term, you can then reabsorb data into this just by shift relations, and then at the end of the day, all you have left is this eta bar. There's no theta term left anymore. So in that sense, the eta prime is, except the scale of this object becomes very different, as I'll discuss. It becomes the eta prime at the end of the day, like this.
But if you take the chiral Lagrangian for say
Yes. Very good.
n flavor, indeed for
Yes.
one flavor, right? Then you write something that depends only on eta. It's the only variable. That's the because
Yeah. So
and the
yeah, I
there is
think-
this log that u that becomes simply log.
exactly.
Right?
Exactly.
So you have a term eta minus theta square, I suppose. But what is the coupling to omega?
Well, so yeah, omega, by the way, is FF dual, right? So
Yes.
so what I'm saying is that if I can do a shift relation, and then essentially I'm replacing using this from the equation of motion, I can just replace the theta entirely by omega over chi, so to speak, right? And so at the end of the day, I'm just replacing this theta dependence by this omega dependence.
So but that equation, the first line,
Yeah.
is it written in the chiral limit? Because you're using.
Yes, this is all in the chiral limit.
But
So what I'm saying is, my point is that to even in the chiral limit, there's a non-trivial susceptibility in QCD. Okay? I mean, even in Yang Mills, right? So
I mean, in Mills I understand,
Yeah.
but in QCD, as you said,
yeah,
there's no theta dependence in the chiral
so
limit.
but you can, but you have to understand that there has to be such a term in the effective
But
action.
that's not the usual chiral Lagrangian, right? That's something that.
Well, it's large
So-
chiral Lagrangian.
so
right?
exactly.
When-
So
Yeah,
this
no,
becomes-
but in the large end, there is no theta square. There is theta minus m and eta square, the whole thing square.
So yeah, but now I'm also working then in the limit m going to 0. Right.
That doesn't-
So
that-
then I would
that-
have a
who
theta
cares?
square.
I mean,
Yeah,
I'm simply
yeah,
saying,
yeah.
I'm taking the expression
Right.
that I find in Weinberg
Right.
and find in Veneziano, I find
Right.
in everybody, right?
Right.
There, for n equal to 1,
Right.
the action is what you wrote except for the last term.
Right.
Like in the last term, there is
Right.
no theta square. There
Right.
is theta minus eta norm square,
Right.
right?
Okay.
Okay.
So
So with
Yeah.
with a
so you can
then you can shift the
exactly. So
the
you can
theta.
use a shift to write it in exactly the form that you're talking about.
Yeah, but
Can you show
I mean-
that slide?
I'm simply saying that
Yeah, I understand what you're saying.
look
Yeah,
that the,
yeah.
the action, I mean, it's has
Right.
this eta,
Right.
Plus there is the anomaly term, right? The anomaly term is eta,
Right.
say minus theta square with some chi in front, right? And
Uh,
then there is the coupling, then there is the theta FFU.
Exactly. So
Right.
now you can use a shift symmetry to write it in exactly the form that
Can
I
I show
talked about.
The shift symmetry in what?
Well, I can shift eta to some eta bar, plus.
Eta plus theta, yeah,
Yeah.
but
So,
nothing
yeah.
changes this coupling. Yeah?
Well, no, because then that would change because then the, or I can, yes.
I don't see
yeah,
how you
yeah.
can have an eta FFUL coupling simply.
Oh, eta F of dual coupling?
Yeah, it's not there.
Oh, so no, that is absolutely critical, as I'm going to discuss. That's a Wess-Zumino-Witten term. The eta bar times F of dual is, so if you look at Veneziano's, this expression is
I think
also there from
I'm just saying
Veneziano.
that the prop of WZW term is the presence of eta in both the term.
Sorry?
No, there is a Zumino term
So
Yeah.
this,
There is a Wess-Zumino term,
now involving also
yeah,
eta.
yeah.
I mean, a term that
There has to be, and I'll show you. So if you give me a few minutes, I'll show you explicitly how you derive the Witten-Veneziano formula actually using this. It's an explicit derivation using exactly this expression. And by the way, so this is also there in the, so there's something called non-net chiral perturbation theory by Leutwiller. And this expression is there, exactly there as well. And there is this theta squared times, that's crucial. So when you do non-net chiral perturbation theory, including the eta-prime, you have an expansion, not only the quark masses and momenta, but also in one array of C. That has to do with this contribution.
Okay, I'm
So,
still
yeah,
confused by
yeah.
this integration of data though. Can we skip that step? You're saying, let's take proper chiral Lagrangian
Right.
in the Lagrangian C limit with
Right.
eta
Right,
with WZW term.
right.
And in that chiral Lagrangian, eta appears as an axion.
Yeah, exactly,
that's-
exactly. In the massless limit, so my claim is that in the chiral limit,
Right.
right, in the pure chiral limit of QCD with massless quarks, the eta prime in the large NC limit is the QCD axiom. Okay, it's when you turn on quark masses that everything changes fundamentally. Okay, that's when the whole CP problem, there's no CP problem in QCD for massless quarks. Okay, there's no theta term, right? It's just, you can just put it equal to 0, or you can just absorb it in the fermion determinant, it's not there. So in that sense, and I'll show you that this term is absolutely critical and so Veneziano never formulated it that way. That's my whole point, is that this leads to an enormous simplicity when you think about this problem, because if you look at Veneziano's papers, indeed, he doesn't formulate it, but this is exactly equivalent. I mean, I derived the Veneziano formula using exactly this formulation.
That's right, but I'm confused because in the chiral Lagrangian, we don't have F anymore, right? Because we're just writing Lagrangian for Goldstone bosons, including eta.
Yes. So the only thing that appears is the topological susceptibility. The topological susceptibility appears.
yes, but that's a function of eta. That gives a mass to the eta, so it's chi eta square.
Right.
It's not
Yeah,
chi theta
no,
square.
as I said, so let me show you.
Yes,
Okay,
that's-
if you're patient, I'll come to the explicit derivation. So what I meant to say is, coming back to the spin of the proton, is that you can write down the spin in terms of an axial vector form factor and a pseudoscalar form factor. These are the spinners, direct spinners. So the axial vector form factor is just a direct coupling of the polarized proton to these virtual photons. So that's this blue blob here. Okay, so this is a direct coupling. But then there's this eta bar massless field that I mentioned. Okay, this QCD axion field, which then decays into two photons from to photon. But then there's another diagram whereby you can have this massless eta bar, which then couples to the QCD topological susceptibility, and then through the QCD topological susceptibility, it couples to these two photons. So these are both contributions that contribute to the pseudoscalar form factors. And so this is the isosinglet sector. So there's axial vector pseudoscalar. So now coming to your question. Okay, let me just, before that, let me just say that the quark helicity in the proton is nothing but twice the isosinglet axial vector current. Form factor, sorry. So the helicity of the proton is twice its axial charge. And then there's also a Goldberg-Tremann relation that relates this direct coupling of this quark helicity, so that's GA, to this pseudoscalar massive eta bar exchange. And so this F is the decay of this eta bar to two photons, and then this is the coupling of the primordial eta bar, which reasons it's an SU2 field, and it couples to the proton and to nucleus. This is the coupling here, and so there is such a contribution. But then, now let me come to the derivation that I mentioned. Okay, so there's also a connection between this eta bar FF dual contributions eta bar to the topological susceptibility, right? So such a coupling is eta bar times FF dual. So to coming to your question, so if you think of the QC topological susceptibility, that can be thought of as a 1 over n expansion of the Yang-Mills topological susceptibility, where this object is precisely this eta bar times FF dual coupling, and that's 1 over n. Okay, so you can do a systematic 1 over n expansion of the QC topological susceptibility, and this object, when you do this 1 over n expansion, results in a shift of this pole. This is 1 over L squared pole, but that's proportional to the Yang-Mills topological susceptibility. When you do this calculation, you see that this is nothing but the Witten-Venugopalan formula. Okay, so to come to your question, okay, you're busy. Okay, I'm just saying that this gives you precisely the Witten-Venugopalan formula. Okay, but that fundamentally involves this eta bar times dual coupling.
To me, it seems that you're counting the topological susceptibility twice. Because I mean,
but you
in the chiral Lagrangian again, there is no FF dual in it. There is just a term of the one.
As I said, you can write down the, as I showed you, you can write down the chiral Lagrangian. The expression that I wrote, right, in the form that I had, can be written exactly in the form that Veneziano had it without FF dual, just in terms of topological susceptibility. In Veneziano's, what's that?
The formula that you had when you integrated out theta instead had an omega square.
Right. It had, yes. So if I go back, right. So it had this structure here.
Yeah, exactly.
Yeah, exactly.
But instead, let's say what you would do in textbooks, right? I mean, when it's to say no, actually. Now you consider omega, you integrate out omega and you get an expression that has just a mass term for eta.
Right, and that, but this is exactly, so look at this thing here. What you do is you do a field redefinition, okay? And you can similarly do a shift of omega by this object here. And when you can re-express this whole thing in this form here in terms of the massive eta prime and a non-propagating blue ball. And if you look at Shore and Veneziano's paper from 1990, that's precisely what they did.
So a non-propagating.
So this G is a glue ball which has no kinetic term. So it's just a normalization of the overall spectrum.
So you can set it to 0.
You can set it to 0. It's just it's part of the normalization of your action. It's not propagating. It's not dynamic. So you can integrate it out if you like your action. And so this expression is precisely what's there in these papers, also by Gia and collaborators. And you can just re-express this exactly in the form that I had here by using a field redefinition. So we can discuss this more. Okay, let me go on. So I'll be
No idea
happy.
what this term theta square comes from.
Sorry?
No idea what this term theta square comes from.
You mean the theta squared? Okay, well, okay. Actually, if you look at Lloyd-Wheeler's papers, you'll see an explicit form of such a term in the Cairo-Lagrangian papers by Lloyd-Wheeler. He writes exactly, precisely this term.
And integrates over theta.
Or actually re-expresses theta in terms of these dual correlates. That's the topological susceptibility. So the building block.
We start with an action that is not invariant under a shifting theta. Then, because that's it, theta is. Then you integrate, and you recover in that way the invariance, right? Because if theta is fixed in your initial action,
right? I cannot do this at all.
Then you integrate in theta.
Yes.
To me, it seems a complicated way of getting the free massive pseudo-scalar.
So actually, it's well, no, because I think, for example, if you look at the usual derivations actually of the Witten-Venugopalan formula, I actually find them much more cumbersome actually than this derivation that we have here, which is just you see immediately that this resummation is what actually gives you a shift in the pole or the susceptibility. And this explains two things. One is, okay, you get the Witten-Venugopalan formula, and also explains in the chiral limit, topological susceptibility vanishes in the forward limit. These are two key results that you get right away in this way. And this is also important because when it comes to the discussion of spin, the presence of this Wess-Zumino-Witten term is very important. So just to summarize here, the quark helicity that I mentioned is something you measure in experiments, is directly proportional to the square root of the slope of the QCD topological susceptibility. And this is a result that Shor and Venugopalan got in 1992, which, as I mentioned, is completely ignored in the literature. And in our framework, we see how this comes about exactly. So you can really show explicitly using the Goldberg-Tremont relation that I mentioned now why slope? Because the reason slope is because the topological susceptibility in the forward limit is 0. So the first non-zero term is the Taylor expansion of that, the first non-trivial term, and that's why it's type. And so here's the result. The quark helicity on the proton is directly related to the topological susceptibility. So I'm kind of running short on time. So there's some very interesting discussions in terms of OZI allowed and OZI suppressed diagrams in QCD. And this object here, so this is the isosinglet axial charge, this is the iso-octet axial charge, and their ratios related to this object here, the topological stability slope. And they really tell you the relation of OZI suppressed and non-suppressed diagrams, those involving just gluon exchanges between quark loops. And you can actually compute this in the lattice. Okay, so in principle, you can compute this object in the lattice. This really hasn't been done because it's very complicated. There are attempts to do it on the lattice. It's non-trivial. People have done model estimates of this, and they are in agreement with existing data. So this is interesting. So I'm kind of out of time, but I just want to mention is that the reason this is also interesting is that when you go to very high energies, this object in the rigid limit is also controlled by the anomaly. And there's an interesting phenomenon, which is when you go to very high energies, there's an emergent scale that appears in the problem due to the close packing of gluons in high energies. So, and this is non-perturbative because the occupancy is 1 over alpha. So think of it as a finite temperature, if you like, because of the high occupancy of gluons. And what they can do is they can induce transitions over the barrier type transitions. So if I think in terms of this topological susceptibility, then there's a corresponding real-time analog of that, which is that of sphaleron transitions. So those are correlators of Chern-Simons of this charge at 2 different times, and that can lead to over the barrier sphaleron transitions. Okay, and so if I write down now this effective action, it has this more non-trivial form. So this is generalizing the work of Venugopalan and others, including this kind of term that I mentioned here. And because you have this temperature scale, you can study it in two different regimes where this scale is less than eta-prime mass or much greater than eta-prime mass. And it turns out that you can actually show that in large-scale classical statistical numerical simulations, which are far out of equilibrium, high occupancy fields, you see such kind of structures where you see that the Chern-Simons charge of gauge configurations clusters around integer values. And you can actually count these sphaleron transitions. And these sphaleron transitions actually scale with the string tension in a very nice way. And this is far out of equilibrium. So these are real-time classical simulations of Yang-Mills, which are far out of equilibrium dynamics, and you see such topological charge, and you can count sphaleron conditions. And so the essential physics that I'm talking about at high energies is like axion-like dynamics on plasma. And actually, so this is again the scaling of the sphaleron transition rate with string tension. And you can actually show that it scales with the square root of string tension in a linear way as a function of time. And you can compute the sphaleron transition rate. It starts out very large, far out of equilibrium, and then it goes to an equilibrium value. And this was actually computed by Arnold, Sohn, and Yaffe some time ago. But at very early times, far out of equilibrium, this system has a very large sphaleron transition. And so I don't want to go into this in great detail, but the way to think about such a coupling, and that's where this picture in terms of eta bar coupled eta dual is important, because then you can think about this object as like propagating the presence of other lots of gluons. And the essential dynamics is that of drag of an axion-like field that's propagating through this medium here of topological susceptibility, and the drag coefficient is what is the sphaleron condition. So what you measure in experiment, that's this object here, the radial limit, is directly then proportional to the eta prime. And this can also be related to eta prime. And what you see is a very rapid quenching of spin, small x. So the way to think about it is that imagine you have a quark, which is going through these gauge configurations. And each of these gauge configurations have some size on the order of 1 over the square root of string tension. But then I also have sphaleron transitions going on, which are proportional to the string tension squared. And so these blobs also carry some topological charge. And so by the index theorem, we know that the helicity flip is given by the difference is proportional to the topological charge, and where the root mean squared is of that is related to the sphaleron transition rate. And so the more sphaleron transitions you have at higher and higher temperatures, if you like, it gives you a larger topological charge. And so as you go to higher and higher energies, what happens is you go to higher and higher boosts, what you see are more of such blobs, which are smaller, but they also carry larger amounts of topological charge. And so the randomization of the spin sort of increases. So the likelihood that you will have spin flips kind of grows as you go to higher and higher energies. And so there's a very interesting interplay between QCD evolution, topological charge, and this dynamical scale of close packed gluons that you see at high energies. So anyway, so that's kind of the, sorry for going over time, but thank you for your attention. We had some interesting discussions.
So this last point, shall I think about it? And also it's related maybe to the Lagrangian. So if you're trying to write some effective action that scales between chiral symmetry breaking and confinement, the confinement transition, when you have both Goldstone bosons and you want to keep gluons, right? Is it somehow?
No, because so what I'm talking about is actually the physics. The physics is still at very short distances, but at very high boosts in the radial limit. So essentially, what happens is you have this very high occupancy of gluons that you see, that the probe sees, and this you can. So essentially, they have a close packing scale, which is given by 1 over the occupancy, and that is effectively like a temperature scale. And so what they do is, so the gluons are very energetic because they don't like to be packed together, and so they have some large, effectively like a temperature, and that's what causes these sphaleron transitions.
So, but that's what I mean. So you want to keep gluons, but at the same time you want to talk
talks
about
to the chiral physics.
So, exactly. So you want kind of to be in the window between chiral phase transition and the confinement phase transition.
Right. So what I'm saying is that even at these weak couplings, there's a non-trivial topological susceptibility, right, of these gluons. And so that non-trivial topological susceptibility will talk to these, so the eta-prime in particular, or the eta-bar. So another way of thinking about it is that if I go back here, the way I would think about it is so essentially I have a topological susceptibility, right? But then I'm measuring this in medium, so to speak, right? So the topological susceptibility is modified by the insertion of additional sources. So think of these as additional sources that couple to the topological susceptibility. And what they do is they don't change the mass, actually. They don't affect the mass of this object, but they do change its propagation. So the eta-prime propagation is affected in this medium here, because of this interaction of large numbers of sources. So it's like thinking about, propagation in a plasma, right?
Yeah.
So if you have an eta-prime propagating in a plasma,
but like in deep high temperature regime, when everything completely deconfined and chiral symmetry is restored,
right?
There is no eta-prime.
Exactly. So in some sense, this does know about chiral symmetry.
So that's what I mean. So you want to be in the window between the confinement and chiral symmetry.
Absolutely.
And that's when
absolutely. I mean, so that's another way of saying it is that this is still kind of vacuum physics. Right. It's not really, so it is. So there's a very interesting interplay, and this is the first such example of this physics of high occupancy gluons and the physics of, chiral symmetry breaking and UA1 breaking. I mean, so normally you would have no problem in thinking about this some people would have no problem thinking about this in language of instantons, right? So you have instanton gauge configurations, which are tunneling configurations you can think of. And so all I'm saying is that when you probe the vacuum at very high energies, very high boosts, so very short time scales, right? The effective occupancy of the gluon interface frame is so large that it can induce these over the barrier transitions. So the saddle point is not an instanton saddle point, but it's really a dynamical saddle point corresponding to these overoccupied gluons. So,
thank you. I think.
Yeah, thanks a lot.
Yeah, but
But thanks for your questions. But
I think that